Hi everybody, I'm Chris Kanish and this is Tricks of the Trade, learning how to learn computer science. Let's get started. Today's lecture is on computing environments. So when we think about computer science and we think about using computers, typically we're thinking about using applications. We're using Visual Studio Code, we're using PowerPoint, we're using an email program or a web browser. These are the things that are directly impactful to our lives. We're choosing to use those programs to do this, that, or the other thing. But there's a whole lot happening below the surfaces there that's really, really important to understanding the full aspect of how computer science works. So we've got our applications, but applications themselves are built using libraries. Now, the difference between an application and a library is that an application is directly used by an end user, whereas a library is something that is used by the author of that application to make writing that application easier, faster, less painful, things along those lines. So for instance, an end user does not use printf. An end user uses a program which uses printf, but they don't use it directly. The author of that program is the one who actually needed to use printf to write that piece of software. Now, just like we're using libraries to make things easier for people who are writing end user programs, there's a whole stack of different components here that rely on each other to deliver that full computing experience. Now, a modern computing environment is going to look a little bit like this diagram I've got in this PowerPoint slide, where there's our applications at the top that we're all familiar with, but they're supported by libraries, and those are supported by a host operating system that serves as the interface between the hardware of the computer, the CPU, the memory, the input-output components like hard drives and network cards, and the actual applications. So the operating system is the part that's in charge of making sure that lots of different programs can use that computer as quickly and efficiently as it possibly can. There's an extra part here where we're talking about guest OSs and hypervisors. One really important part of modern computing that every computer science major should be familiar with is virtualization. This is enabled by a special thing called a hypervisor, which allows different operating systems to multiplex access to the hardware. We're going to get into a lot of those concepts later on in your degree. But for now, simply understand that this is what that layering looks like. Now, I actually don't care which operating system you're going to use over the course of your computer science degree, over the course of any given individual course. What's important to me is understanding how those operating systems are put together. Typically, an individual class is only going to be taught in one specific operating system, or maybe it's in a programming language that's available across lots of different operating systems. We're going to be learning about operating systems and how they provide services to applications using the Linux operating system. There's lots of different operating systems. As I mentioned on that first slide, they cooperate with the CPU to run the programs of the user. Programs that are compiled for one operating system are typically incompatible with others. We have both desktop operating systems as well as mobile operating systems. There's nothing fundamentally different about them. They were designed at different times for different purposes and thus have different abstractions of how users are expected to use them, what types of hardware users are expected to use them on top of, things along those lines. Typically, we're only going to have one operating system per machine, but sometimes we can actually multiplex those and run more than one operating system on more than one machine. A lot of the times that students pick which computer or which operating system to use, usually there's a lot of talk about how Mac OS and Linux are very similar, but then Windows is a little bit different. There is a reason for that, and it's pretty complicated, but one of the biggest components of that reason is the POSIX Portable Operating System Interface. This is a set of standards used for defining how different programs can interact with their operating system. You can actually have POSIX compatible code running on Windows as well as on Linux and Mac OS and lots of other variants of Unix. They all are programmed to this specific interface. And when you program to that interface, you can actually run that program cross-platform. For the purposes of CS361, if you're watching this lecture for 361, some programs are kind of going to be usable in a fully Windows environment, but usually it won't work for our purposes in class. Actually, basically, it will more or less never work the way that we want it to, because we're going to be using very low-level abstractions provided by the operating system, rather than programming for an end-user application that can get away with being cross-platform simply using the POSIX interface. Libraries are, in general, the ways that we as computer scientists, as programmers, are interacting with the operating system, are interacting with the computer that we are running on top of. Libraries themselves can be cross-platform. They can provide a specific functionality in C on Windows, as well as C on Linux or macOS. POSIX itself is a set of standard library interfaces that do exactly that. You can write programs that use that POSIX interface, and they will effectively use that same library implemented in different ways for different operating systems and accomplish the same things. Libraries are used for lots of different things. Instead of just really, really basic stuff like printf, it can also be used for really, really complicated stuff like machine learning. One funny joke that you'll see, I've got a XKCD up here where Python is known for having lots and lots of libraries that implement dozens of just ridiculous functionalities. I don't want to explain the entire joke, but the basic idea is that anything you want to do in Python, you're just one import statement away from doing. Now, arguably even more important than understanding how libraries work and how they fit into computing is the shell. So every computing environment has something that functions as a launcher, something that functions as a shell or an explorer or a finder, something along those lines. You have some program that's always running that allows you to launch other programs. All of these things are more or less newer versions of what has historically been called a shell. So command line interfaces are the original and still very effective way for computer scientists to use computers. And it's still one of the most powerful ways that we can use our computer. I'm going to show that a little bit later on. And it's also commonly the only way that you're going to use a computer that is, on campus. Maybe it's in Amazon's cloud or Microsoft or Google's cloud. The shell is an incredibly important thing, and that's going to be one of the focuses of this Tricks of the Trade module. Now, when we're using shells, one of the most important things that we're going to do with it, obviously, is run programs. The shell itself is not a program that we actually want to use to do useful work. It's a program that allows us to launch other programs that allow us to do useful work. And one of the important things that you're going to get out of a shell is it's going to find your programs that you're running in any sort of directory where programs can potentially live. That path is something that's both available in Linux and macOS in this path environment variable. And even on Windows, you do have a path environment variable if you go into your environment variable settings. On all these different operating systems, another important thing for computer scientists to know how to do is how to get new executables. And the kind of non-computer scientist-y way to do this is you Google for the program, you download the program, you double-click on the program, and you install the program, right? That's usually how you're going to get software in a traditional computing environment. What typically will be done in a more professionalized software engineering style environment is the use of package managers, where you're actually going to keep track of everything that you have installed on your computer through a centralized piece of software. On Windows, there is the chocolatey package manager. On macOS, there's the homebrew package manager. And on Debian-derived Linuxes, there's the apt program manager. All of these are incredibly useful for both keeping track of the software that you're downloading and running, as well as installing new stuff. Another awesome part about modern package managers like this is that they're generally providing free software. Right? Almost everything that's in these popular package managers is just free software. So if you need a program that does blah and you see that it's in Chocolatey or in Homebrew, you just type in what you're supposed to do to install that program and you've got it. I would highly recommend anybody that's doing computer science on any of these different environments, whether it's Linux, Mac, or Windows, to install a package manager and use that to download and run the software that you're going to need for whatever it is you're doing. So far, we have the pieces that we use to build programs, libraries. We have a way to launch those programs, including where to find them, and a way to get new ones. Now, we just need to know a little bit about all the things that happen between the line of code you write and the instructions getting fed to the CPU. This part of the computer is called the kernel. One important part of modern computers is that they can run more than one program at a time, and this poses a problem. How do you let multiple programs run without interfering with each other? The basic answer to that problem is to create computer systems that operate in two modes: user mode, where individual programs run their code and are restricted in what they're allowed to do, and supervisor mode, sometimes called kernel mode, where the operating system coordinates the execution of different programs, all trying to use the same computer at the same time. The operating system is responsible for maintaining this isolation, so for instance, if a program crashes while it's writing a file to the disk, it doesn't corrupt your entire hard drive, just the file it was working on. The kernel is a little bit like a library where it doesn't get anything done itself, but instead it helps your programs do useful things. However, libraries are just more user mode code. They can't do anything special. They just make your job easier by letting you use previously written code to accomplish whatever you're trying to accomplish. What's special about the kernel is that it has full access to the hardware of the computer. This full access allows the kernel to do things that normal applications can't, like start, stop, pause, and resume applications running on the machine, and directly interact with the hardware of the computer, like the hard drive or other peripherals. While the code to manipulate the core components of the computer, like the CPU and RAM, are directly part of the kernel, we need to use device drivers to interact with other hardware that you attach to your computer, like graphics cards or drawing tablets. Directly interacting with these things usually requires supervisor mode code to be able to use them efficiently. You can kind of think of them as third-party software for supervisor mode, just like apps you download off of the App Store are additional programs that you can download for user mode. These device drivers don't accomplish anything themselves. They help you use the custom parts of your computer through being part of the kernel, which is just a piece of software that helps your applications use all parts of the computer. While on the topic of kernels and operating systems, there's one slightly more advanced topic that has taken the world by storm in the last decade or so, and at this point is built into all modern desktop class operating systems, and that's virtualization. Virtualization is the ability to run an operating system inside of your operating system. Pretty cool, right? This allows you to use one physical computer as several virtual computers, just using the software that's built into it. We won't go into the details of how that works, but just what it does. Virtualization relies on a hypervisor. While hypervisors used to be provided as separate pieces of software like VMware or VirtualBox, over the past 5 years or so, hypervisors have been integrated into the operating systems themselves. The three I've listed here are the basic built-in hypervisors for macOS, Linux, and Windows. The first cool thing about virtualization is that it allows you to run different operating systems on the same computer at the same time. Because Windows, macOS, and Linux are all fully compatible with the standardized x86 processors that Intel and AMD make, the hypervisor can share the hardware between these operating systems without too much performance loss, which is really impressive if you think about it. Recall from the last slide that one of the most important tasks of a kernel is to provide isolation between different processes. One other super cool thing about being able to create multiple virtual machines is that one virtual machine lets us crank our isolation up to 11. Rather than just isolating individual processes, we can isolate entire computers, which is super useful when you want to use one machine to do a specific thing, like act as a web server or a Minecraft server. Virtualization is a tool that we can use to create these environments, but it can't do the whole job for us. So when it comes to virtualization and package managers and libraries and environments, what's really important about creating environments, especially when you're a computer scientist, is keeping them straight. One thing that language package managers allow you to do is to create self-contained environments where only specific libraries or only specific packages are installed. That allows you to make what works on your machine work on some other machine, where in a typical non-computer scientist computer, they download this thing and they download that thing and they run this thing and they run that thing, and a specific thing doesn't work correctly. And you say, okay, well, I'm going to try and do that on my machine and I'm going to have the same stuff installed, and then I run it and it works. So it didn't work on their machine and it works on your machine. It's really, really hard to figure out all the different ways that their machine differs from yours to try to debug that. What is the standard way of doing this in computing nowadays is to have a declarative environment where you say, here is how you go from an empty install of a programming language or an operating system. Here's all the things that you're going to change to it to get to a specific state. The most powerful and useful way to do that, to define a specific environment like that right now, is Docker Desktop. One of the main things here that we get is that this is more or less a Linux-only environment definition tool. There is a way to do it for Windows, but we're not going to worry about that. The main thing that we get out of Docker is that we can create an environment. Now we're using virtualization to create this on any modern operating system. So you can use the Beehive virtualization to use Docker Desktop on Mac. You can use Hyper-V to create Docker Desktop on Windows. And you'll be able to use whatever libraries you want within that Linux environment. You'll be able to use a shell in there. So the amazing thing that we get out of using Docker Desktop in a lot of the classes that I teach, at least, is that we have this declarative, specific, standardized way to talk about a specific environment. What we're trying to prevent is you saying, oh, it worked on my machine, and me saying, oh, I tried the same code and it didn't work. What this allows us to do is to say, if you're on a Mac, you install this. If you're on a Windows, you install this. If you're on Linux, you install this. And we have a definition of here's how to exactly create a standardized computing environment that has all of the same libraries, installed all the same ways. And if it works on your machine, the hope is that it's going to work on everybody else's machine. So what we covered in this lecture today is the idea of a library, the idea of an operating system, the idea of a hypervisor, and the idea of shells and paths. We're going to go into a lot of those topics in more detail later on. Thanks so much for watching, and I'll see you next time.